Hello everybody, welcome back to my channel where we solve difficult integrals, and today's integral is a very tough one, which is the Vardi integral. This integral has already been solved on many YouTube channels, but for what I saw, all of them use the Kummer series, which is a cheat code discovered by Kummer but first Melson, but anyway, which is the series of log n divided by n times sine of 2 pi n z, which can be linked to the logarithm of the gamma function, which is a cheat code I don't want to use because we already saw that on other channels, so we're going to use another method to solve this integral. And this method uses Stieltjes constant and the Hurwitz zeta function. So here we go. First, we do the substitution. X equals logarithm tangent theta. Then we see immediately that theta equals arctangent of e to the x, and if we differentiate, d theta equals e to the x dx divided by 1 plus e to the 2x. Then our integral v equals the integral of, well, from where to where, and pi by 4 theta goes to 1, so tangent theta goes to 1, so x goes to 0, and in pi by 2 theta tangent theta goes to infinity, so x goes to infinity as well, positive infinity. So we have log of x times d theta, which is e to the x dx by 1 plus 2x, e to the 2x. Now let's introduce a special function which is called the beta function, but the smaller beta function, which is a Dirichlet function defined for one argument, let's say s, by the summation for a n greater or equal to 0 of -1 to the nth power divided by 2n plus 1 to the s power. And we can prove, I'm not going to do it right now, but we can prove it, that beta of s equals 1 by gamma s times the integral from 0 to infinity of x to the s minus 1 times e to the x divided by 1 plus e to the 2x dx. We can just do a series expansion in this integral, and, well, the proof of this formula is pretty easy, but anyway. Then what we see that here we can try to use a Leibniz rule. If we differentiate with respect to s, we get some logarithm of x, e to the x as we need, and 1 by 1 plus e to the 2x as we need as well. So we can link our integral v to the derivative of the beta function. How do we do this? We call a function, let's say I of s, being equal to beta s times gamma s. Then I of s is just this integral here. And we see that if we differentiate with respect to x to s, we need the case s equals 1, because then we have x to the 0th power, and we get here not any power of x, so exactly what we need. So we need the particular case v equals I dot of 1, which is, when we see this, we can calculate the derivative of the I function, which is exactly beta dot of 1 times gamma 1 plus beta 1 times the derivative of the gamma function, which is gamma times digamma. So gamma 1 digamma 1. And here gamma 1 is nothing but 1, gamma 1 equals 1 again, and digamma 1 is negative, well, gamma again, but the Euler-Mascheroni's constant gamma, which is negative 0.577. Anyway, now we have expressed our integral v in terms of beta stuff only, and well, a non-constant, the Euler-Mascheroni's constant. So we know that v equals beta dot of 1 minus gamma times beta of 1. And our goal is now to express beta 1 and beta dot of 1, which is not quite easy, but, well, still doable. How do we do this? We first express beta in terms of an other function, the Hurwitz zeta function. How do we do this? We start from our expansion here. Beta s equals the sum of negative 1 to the nth power by 2n plus 1 to the s. And, well, the Hurwitz zeta function is defined by, for two arguments, s and alpha, let's say, by the sum for n starting at 0 of 1 by n plus alpha to the s power. So we see that if we calculate zeta of s 1/4 minus zeta of s 3/4, we get the sum for n starting at 0 of, well, here we have always 1/4 to the s power, so we can just take out a 4 to the s power, and we get 1 by 4n plus 1 to the s power minus 1 by 4n plus 3 to the s power, and all this multiplied by 4 to the s. Yeah, that's it. And here we see that we recognize the term of our beta series, because here for n equals 0 you have this term, for n equals 1 you have this term, for n equals 2 you have this term, but for n equals 1, and etc, etc. So we have here 4 to the s times beta s, which proves that beta s equals 4 to the negative s times zeta s 1/4 minus zeta s 3/4. And we need the case beta 1, which is the limiting case s goes to 1 of beta s. Why? Because even though beta 1 exists, beta is a continuous function, we expressed it in terms of zeta stuff, which only exists if s is different than 1. Because otherwise, zeta s anything is a divergent series, so we need the limiting case, and then because we have zeta here minus zeta here, this function exists even in 1. Well, at least converges to a real value when s goes to 1. So here let's call this strange function the delta function of s, and what we need is beta 1, which is here just let's s equal 1, and you have delta 1 divided by 4. And now what? Now we use the series expansion of the zeta function, and this series expansion is zeta S alpha equals 1 by S minus 1 plus the series, well, it's a Laurent series, not a Taylor series, but anyway, it's the series for n starting at 0 of negative 1 to the nth power divided by n factorial gamma n of alpha times s minus 1 to the nth power. We have here a term called the Stillches constant, or Stillches function, which is defined this way. Gamma n of alpha is the limit for, let's say, m goes to infinity of the sum for k from 0 to m of log to the nth power of k plus alpha, all divided by k plus alpha minus log to the n plus 1 of m plus alpha divided by n plus alpha. This is a hideous function. For any n or alpha, it's absolutely horrible to just find any value at all. But we're very lucky. We're only looking for the particular case s goes to 1, and if s goes to 1, then this term goes to 0 when s is when n is big enough. So here you see that for any n greater or equal to 1, we have this goes to 0. So for the first term we're looking for, we only need the first case gamma 0 of alpha. Why do I say this? Because here you see that delta of s is just a difference of data stuff here, and so we're only left with the sum here because this term doesn't depend on the second argument, alpha. So we have the sum for n starting at 0 of negative 1 to the nth power divided by n factorial s minus 1 to the nth power gamma n to the 1/4 minus gamma n to the 3/4. And if you let s goes to 1, all this vanishes for n starting at 1, so you're only left with the first term, which is negative 1 to the 0th power divided by 0 factorial, which is 1. And here you're left with gamma 0 of 1/4 minus gamma 0 of 3/4. So you have gamma 0 1/4 minus gamma 0 3/4. Now we need to express gamma 0 in terms of other functions. How do we do this? We just use the development here of gamma n, and we let n equals 0. We get now gamma 0 of alpha equals the limit for m goes to infinity of summation k starting at 0 to m. Here log to the 0th power is 1 by k plus alpha minus here n equals 0, so you get only divided by alpha. I missed something, sorry. Here is not alpha in the denominator, it is 1. Much better, much better. So here n plus 1 equals only 1, and you have log m plus alpha. When we see this, we see the difference into a harmonic series and a logarithm. So what we need to think about is the digamma function. And well, let's say we can just express this sum in terms of digamma stuff, we know that we use the relation digamma n plus alpha minus digamma alpha equals the sum for k from 0 to n minus 1, 1 by k plus alpha. So here gamma 0 of alpha is nothing but the limit for m goes to infinity of here digamma n plus 1 plus alpha minus digamma alpha minus log, no, here it's not n, it's m, minus log m plus alpha. And we use the fact that digamma z is equivalent in infinity to log z, so when you have the limits, this term and this term cancel out and you're left with digamma alpha. So gamma 0 of alpha is nothing but the negative of digamma alpha. Well, this is not completely true because log z is equivalent to digamma z, but we know digamma z equals log z plus capital O of 1 by z, so this works anyway. Doesn't matter so much, so delta of 1 is, let's remember, gamma 0 of 1/4 minus gamma 0 of 3/4, which is nothing but digamma 3/4 minus digamma 1/4. Now we use the reflection formula for the digamma function. Digamma 1 minus x minus digamma x equals pi cotangent of pi x. So here obviously x equals 1/4, and you have cotangent of pi by 4, which is cosine square root 2 by 2 and divided by sine square root 2 by 2 as well. So this is 1, and you have here this equals pi. So delta is nothing but pi, and beta 1 is pi by 4. Now we get back our expression of the beta function because we need the derivative of the beta function. So we have beta dot of s, which is well, product rule here, derivative of this, it's negative log 4, which is negative 2 log 2, and then derivative of this, so we have 4 to the negative s times, first we differentiate delta, so we have zeta dot, well, I should say delta 1 0 of s 1/4 minus zeta 1 0 of s 3/4 minus 2 log 2 zeta s 1/4 minus zeta s 3/4. But we know that if we differentiate with respect to the second argument, the short zeta function, we get nothing but the zeta function itself, but another argument. So the second derivative, well, the derivative with respect to the second argument is not very useful. So we can just let zeta dot being always zeta 1 0. It will be much easier, and then we have delta dot of S, and here again delta of S. So beta dot of S, of 1 is nothing but here you let S being equal to 1, and you have delta dot of 1 minus 2 delta 1 log 2 all divided by 4. Again, we use this expression, while you have here a difference, not in here, we already know this value. This expression, you have a difference, so here the 1 by s minus 1 cancels out, and here you have again gamma n alpha minus gamma n beta, but you differentiate. So when you differentiate, the first term vanishes because it is independent of s. So here n equals 0 doesn't matter. N equals 1 is the only term that matters because we have s minus 0, which is usually different as 0 to the 0th power. While we have differentiated because here we have n minus 1, here we have the n which goes out, so, and here which will partially cancel out with the n factorial. So you have n equals 1, which is important because here you have the power which is equal to 0. And what is this term? It is here 1, here 1, here negative 1, so you have negative gamma 1 of alpha. And for n greater or equal to 2, this goes to 0, and this is a finite expression because this function never goes to infinity in an real number. So delta dot of 1 is here 1, 1, negative 1 equal to negative gamma 1 of the second argument, so 3/4. Well, now we have the negative here, so 1/4 plus gamma 1 of 3/4. Okay, so no error for what I see now. So okay, just here gamma 1 3/4 minus gamma 1 1/4. And well, now the problem is we cannot express the gamma 1 function in terms of other functions like the digamma function for what we did for the gamma 0 function. It is not possible here, but we're lucky. We only are looking for rational arguments. Here 3/4 and 1/4, and we have a Armstrong formula for rational arguments, and especially a reflection formula, which will be very useful in our case, which is the development of gamma 1 m by n minus gamma 1 1 minus m by n, which is 2 pi times the sum for k from 1 to n minus 1 of sine 2 pi mk by n log gamma k by n, and outside of the sum minus pi times gamma plus log 2 pi n cotangent m pi by n, which is a little cheat code again, but well, we cannot calculate this integral without using a cheat code, so This is a new one, at least, I guess. I hope. So now we have to calculate our finite sum, and here our cotangent stuff. So nothing particularly difficult. Here for k equals 1 we have 2 pi, well, first of all, we have to evaluate m and n. Well, we could use absolutely any m and n value that works. We only need n greater than 1 than m, but here, well, you can do pretty much whatever you want. Here n equals 6 and n equals 8, but if any values work, let's just take the smaller one, the smallest one. So here m equals 3, n equals 4. So you have here 3, 1, 4. You have 6 pi by 4, which is 3 pi by 2, which is -1. So k equals 1, you have -1. K equals 2, here you have here 2, 3, 2, 12 divided by 4, which is 3 pi, so a integer number times pi, so the sign equals 0. And for k being equal to 3, which is n minus 1, the last term, we have here 2, 3, 3, so 18 divided by 4, so 9 pi by 2, and you can subtract 2 pi's 4 times and you get pi by 2, so the sign equals 1. Which is pretty logic. If you have here -1, 0, then the next number is always obviously 1. Anyway, and here cotangent is 3 by 4, so up here the sign is positive, cosine negative, so you have -1. So delta prime or dot doesn't change so much. Unexpected. Delta prime of 1 equals 2 pi times our sum, which is here -1 times log gamma 1 by 4. And here plus log gamma 3 by 4. Here -1, so +1 plus pi times gamma plus 8 pi, which is log 8 plus log pi, which is 3 log 2 plus log pi. Alright, thanks to the reflection formula for the gamma function, we know that gamma 1 minus theta gamma theta equals pi cosecant pi theta, which proves that gamma 3/4 gamma 1/4 equals pi cosecant of pi by 4, which is square root 2, so pi square root. So here, if you express this as a quotient thanks to the log property, you have gamma 3/4 divided by gamma 1/4. And gamma 1/4 is nothing but pi square root 2 divided by gamma 3/4. So you have here the divided by gamma 3/4, which is in the denominator there, in the denominator of the denominator, so which goes to the top of the fraction, and you have 2 pi log gamma squared 3/4 minus log pi minus log square root 2 plus pi gamma plus 3 pi log 2 plus pi log pi, And now we get back to our initial integral, which is v equals beta dot f1 minus gamma beta 1, which is delta dot 1 minus 2 delta 1 log 2 minus gamma delta 1 all divided by 4. Delta 1 is nothing but pi, and here we have delta dot 1, so so here you have 2 pi log pi, negative with the negative sign. Here 3 pi, here pi log pi, so this and this goes to, we're left with negative pi log pi. Negative pi log pi. Here plus pi gamma cancels out with here gamma times pi, so this and this cancels out. Here you have negative 2 pi log 2, and here we have plus pi log 2, so this and this goes to pi log 2. And here you have log square root 2, which is 1/2 of log 2, and here 2 pi times 1/2, so we have here negative pi log 2, here 3 pi log 2, and here negative 2 pi log 2, so this and this cancel out, so you don't have any log 2 and the final expression. And here the log gamma squared, we can just take the square root outside of the logarithm, and we're left with 4 pi log gamma 3 by 4, and while this is divided by 4, you have log gamma 3 by 4 is taken outside of the fraction, and you have negative pi log pi by 4 plus pi log gamma 3 by 4. And this is our final expression. This integral right here equals pi log gamma 3 by 4 minus pi log pi by 4, which is, in my opinion, one of the most incredible results I ever found in my entire life of mathematician. And well, I really like this integral. It's a very, very, very tough one, and I guess we won't do the integral as difficult as this one, because this is a very tough one, too much time needed to solve it. So in the next video we will solve not integrals for once, but we will solve series expansion in order to evaluate some series involving digamma and trigamma functions, and we will use very interesting results, as for example the value of the series of here sum hn by n squared, where hn equals the sum from 1 to n of 1 by k, which can be linked to the zeta function, the Riemann zeta function for once. And well, this is very nice. It will be, I hope. See you in the next video, and until then, study, learn, progress. See you next time.